Thank you, and thank you to the organizers for inviting me back again after 20 years. I can't believe I've been involved with OPLSS for so long, but it is really wonderful to be here, and I'm looking forward to chatting with many of you over the course of the next few days. So yeah, my name is Steve Zdancewic. I'm going to be telling you about things related to formal verification of monadic computations, which is kind of a mouthful. By the way, this is not what I presented 20 years ago, so it's actually relatively fresh material in the grand scheme of things. But before I jump into it, I want to thank the many students and collaborators that have sort of helped me develop the content for this presentation. They deserve a lot of the credit here. Also, I know that OPLSS is you're in your second week of quite a heavy program of lots of content, and I'm not going to spend a huge amount of time on motivating what I'm going to tell you about, because I think you've probably seen a bit of this maybe several times. And I think Steve has already started, just the last talk, was already starting to talk about security-related issues. But a lot of what motivates my work is, and has for the last 20 years, is trying to build more reliable, higher confidence kinds of software. And I like to do that by using programming language technologies to reason about interesting systems of computation. So now I don't have to argue too forcefully to convince you that things like operating systems and compilers and the kinds of mission-critical code that might be controlling your car or airplane and so on are important to get right. And so a lot of my work in the last 10 or 15 years has been about that kind of verification. Of course, these are complicated things to implement and complicated things to design. They have very complicated specifications and very complicated kinds of behaviors. Most of them not quite as simple as the imp language that we're going to visit again. So it's very hard to give an OPLSS talk without visiting simple PL semantics. But one of the I think quite encouraging things in the last few years is that we're starting as a community to really see how to use ideas from programming languages to address these, and in particular applying formal verification of the kind that I won't be able to teach you how to do in four lectures, but I can kind of give a high-level tour of over the 4 lectures to give you a kind of sense of what it might take to do things like verify the correctness of a compiler or an operating system, or just programming language semantics, or to check the soundness of a type system with respect to its information flow security policies, for instance. And so you can see many, many success stories over the years. CompSearch was extremely, the verified C compiler implemented in Coq was one of the very inspirational projects when I was starting to get into formal verification more than 15 years ago. And you can see many since then. So these lectures, and I'll explain why I'm kind of having to juggle the size of my slides in just a second. These lectures are a kind of particular take on one interesting approach to verifying these kinds of systems. In particular, how do we implement and reason about so-called monadic programs? These are effectful programs. In the Coq, soon to be renamed ROC theorem prover. I'm going to just keep calling it Coq. It still hasn't been officially vetted, and I think that wouldn't happen until July anyway, but and all my slides already say Coq. So I'm going to stick with Coq for now, but I'll be looking forward to the change. This particular slice of topic or sort of content is going to touch on many things that you've probably seen already a bit here at OPLSS, hopefully this will echo some of the things you saw last week and some of the things that Steve and others are talking about this week. So in particular, I'm going to, as I said, we're going to jump into formalizing semantics with IMP according to the informal poll Steve did just a few minutes ago, many of you are quite familiar with, say, the large step operational semantics and import. I'll show you the small step version of them. I'll show you them in Coq. I won't dwell too long on it because I want to point out some of the pluses and minuses of representing programs in that style, which will actually motivate monads and monadic reasoning in a nice way. We'll take a tour through thinking about what it means for two monadic computations, two effectful computations, to be equivalent. Actually, this is perfectly in sync with what Steve was just alluding to with the information flow. This notion of information flow security can be seen as an instance of the kind of reasoning we'll be doing. But we're going to sort of take a sharp left and not think about security, but instead think about reasoning about non-terminating programs, interactive programs, things like non-termination, which will let us build an imp semantics rather than operationally, denotationally. And this will give us another way of reasoning about the semantics of the programs, formalizable in Coq. And we'll talk along the way about how to do relational reasoning about these types of representations, and I hope to connect it to things like the security equivalences that Steve will be talking about. But we can also connect it to things like program verification and optimizations and reasoning about the correctness of particular programs. And then depending, so my goal here is to explain as much of a prefix of this as I can to you over the next 4 days, but I would rather do it thoroughly and, so that you understand the things I'm trying to say rather than get to my last few bits. So please do ask questions. That's part of the plan here. But if I have some time at the end, I'll show you how we sort of scale up the ideas that I'm sketching in these lectures to apply them to the verified LLVM project, my Vellum project that we've been working on at Penn for quite a while. So that's the plan. Any questions before I sort of launch into technical content? I did this survey before the last week as part of the course. I thought I would show you the responses because I found it kind of enlightening. It also explains why it's going to be a little hard to thread the needle on the topics here. So general programming language knowledge, almost everybody here, not surprisingly, is interested in lots of different kinds of programming languages and technologies. So very high coverage of most of the programming paradigms. People were happily adding dependently typed theorem provers as extra options. I found the most interesting one I had never heard of, culinary-oriented. I've never heard of that. I would love to learn more. That's very cool. Monads, it's a little bit more mixed. About 10% of you are proving monad laws and things like that. About 30% altogether, 40% altogether have some pretty familiarity, but 60% of you are maybe not so comfortable. So we're going to dwell on that for a bit. I'll give you my version of an intro to monads and monadic programming. I don't like the burrito analogy. And then here is what the responses were for Coq lean interactive theorem provers. It's a pretty flat distribution with maybe a little bump at the end, which again, maybe not surprising for OPLSS, but I'm not going to assume too much background on Coq or Agda or any of that sort of thing. And rather what I've chosen to do is I'll show you some Coq syntax. I'll present my, present all of my material based on a Coq formalization. You're free to ask questions and I can motivate things by how we would do this in a theorem prover. And then I'll also give you a tar file of all the lecture content actually with augmented material, more monads, more exercises, that sort of thing, which is sort of a work in progress version of Software Foundations if you want to dig deeper and learn more about Coq, that sort of thing. And just to complete the survey, here was the sort of familiarity. So reasoning about programs in a formal way is one of the themes of OPLSS. I'm sure you've already talked about things like logical relations that you can use to justify the correctness of some reasoning principles. Steve will probably talk about type systems for information flow security. I'll talk a little bit about Hoare logic or program logics, which are more geared towards proving functional correctness properties of individual programs as opposed to meta-theoretic properties about the entire programming language. But I'll try not to assume too much background on any of that. So that's just to kind of make sure we're all on the same page about backgrounds. So as I said, that's kind of what I'm going to aim to do. And let's jump into it. Oh yeah, this slide is just to remind me to say that I wasn't able to authenticate to my to put it on my webpage yet, but as soon as I get good access to both my cell phone and the internet, I'll put the course material for this series on my website and put a link to it in the OPLSS Slack. And as I said, this is, if you really want to dig into the content, this is sort of a work in progress volume of software foundations covering things about monadic computation and interaction trees and sort of reasoning in the style that I'm going to tell you. And I would welcome your feedback. Good. I've already alluded to lots of connections. So Coq is a dependent type theory. So if you're interested in that, you hopefully will get things from that angle. I'm assuming Amal covered logical relations in her material. We'll see instances of logical relations that are used in reasoning about this code, and I'll point that out. Information flow and probabilistic programming, as being covered by the other Steves this week, can be seen, they have very strong ties to the monadic style of representing behaviors that I'll tell you about. So just keep these things in mind as we go forward. Good. Any questions before we really begin? All right, so as is apparently traditional, I'm going to start with IMP. So this is going to motivate, so what do we want to do? We want to, if we want to mechanize the semantics of IMP in a theorem prover like Coq, and then use that semantics to do interesting things like prove equivalences between programs or maybe reason about the non-interference properties of the semantics or something like that. The first step is to give some kind of representation of the language semantics. The usual first step to doing that is to define the abstract syntax as some kind of formal data type. And so this is a variant of the IMP abstract syntax, as you might write down using BNF grammars. This is the Coq notation for the commands part of this data type, as taken from the Coq formalization. So we'll be seeing quite a few of these sort of Coq-like definitions in my slides, so please do raise questions if you have any. And the reason why I keep having to like rezoom things is because, as I said, all of these slides are extracted automatically from the Coq development, so it's sort of a literate thing, and the markup is a little bit uneven between different slides. So if I have to sort of zoom and readjust, it's because it's really intended that you go download the Coq development. You can step through all of it interactively in the theorem prover and really investigate all the definitions step by step. OK, so with that preamble, here's what we see. Here's how we write down the data type of commands, which are just skip, assignment, sequencing, if, and while. This is just how you would write down this data type in Coq. The keyword inductive tells us that it can be, we can define the sequence of two commands recursively in terms of command itself. Okay. I'm going to try to breeze through this sort of thing pretty quickly. So just as an example, Coq has very good facilities for introducing notation, user-defined notation. So that's what these little curly demarker brackets do. They put Coq into a mode where you can write more natural-looking syntax. And so this is legitimate Coq, where these funny curly bracket delimiters say, parse this as an IMP. I'm not going to get into the details about how you can do that. It's all in the development if you want. I just wanted to show you that this is how you would write everybody's favorite factorial function, calculates factorial of x using a while loop. and this notation would be desugared into these command data types by that notation. Okay, so we can use this example code as a running example. All right, and just to show you, for those of you who haven't seen an interactive theorem prover before, there are quite a few of you who weren't so familiar necessarily with how this works. This is Coq in Proof General, which is one way of interacting with it, where for the sake of example, I have defined this factorial function, this code here. I've actually, so that's between, this part is just what we saw on the slide. That's the syntax for the factorial code written in this Coq notation. We might like to prove some notion of optimization correctness, which would say that, oh, that while loop up there terminates and actually produces some program state that is the same as what you would get if you ran this imp program, which happens to be, retain the fact that x was 5, z gets decremented to 0, and then y ends up with 5 factorial, which happens to be 120. So this equivalence notation here, we were going to have to formalize what that means, but it basically intuitively is supposed to capture that these two programs do the same thing when we think of them as imp semantics. And in Coq, we can interact with it. You see the parts here in blue have been type checked and verified. I'm just about to enter this sort of proof mode, where you can see over on this side, I have a goal, which is to prove those equivalences, that equivalence. Well, this is just restating the same thing, but slightly less pretty because I had to make the font too big for making it. Okay, but how would we do this? Well, it turns out that I will show you over the course of the next few lectures, we can do things like implement an optimization, for instance, loop unrolling and constant folding and constant propagation. And if we do some amount of that, then we can prove, and we prove them sound. So we prove that they preserve the equivalence of the meaning of these programs. Well, it turns out that the factorial function on the left is equivalent to apply 6 iterations of optimization to that program. That's just a step of reasoning that I'm doing interactively in Coq. And then I can say, okay, call by name. So that's call by name evaluation of the term representing the optimized version of that code. So you'll see that the optimize 6 went away. And the result of that particular optimization pass is the code that's maybe a little bit ugly up here, where it unrolled the loop, did some constant folding and constant propagation, did some simplification, and ended up with this straight line sequence of assignments. And by the way, we proved that that is sound, so it should guarantee the same semantics. Then we can do another optimization pass. I split it out. Of course, we could package it all together as one thing, but it's less of a cool demo in that way. We could prove a classic compiler optimization like dead store elimination. If you look in this first thing here, like here's a store to z gets 5, but then later z gets 4 because we unwound the loop. And then later z gets 3 and 2 and 1 and so on. So if we apply a dead store elimination program transformation, well, I've proved that correct as well. And so if we simplify that, we end up with something that's looking pretty good. And it just so happens that the base case of that particular optimization leaves a skip at the end, which is obviously, any command followed by skip should be equivalent to the command. That's a kind of a simple lemma that we proved correct. And now we've gotten to the point where actually, if I make this a little smaller, they're the same program. And so now we can conclude by reflexivity that those two programs are the same. And Coq will have verified that particular program transformation. And optimize and dead store elimination we could apply to other imp programs. And because of the soundness theorem that says that those are correct, and we would have high confidence that we aren't changing the meaning of the code. Okay, so that's sort of a tour of the kinds of things that you can do. Of course, IMP is in some ways a toy programming language. To make it realistic, you have to scale it up to things like a heap model with interesting data structures and aliasing and having go all the way to something like C. And this gives you a sense of how you would do verified compilation or verified program transformations in something like Coq. Okay, so that's sort of where I would like to get you over the course of the lectures, give you a sense of how we prove these optimizations correct, how we represent the reasoning, and also I'll show you some other things. So this is just one example of the kind of reasoning we could do, prove these two programs equivalent. We could also prove something else, like maybe the fact that x is 5 before and after, or x's value is unchanged. That's a true fact about this code. We could prove that sort of thing as well using a program logic that would allow us to reason about the, the initial and starting states of the program. Question? Yeah?
Yeah, I'm just curious. You mentioned that you could package a bunch of these rewrites together and make it really short. But I'm curious how much, if any, of this could be just automated away through one of the stronger tactics?
Sure, yeah, actually, that's a great question. So the question was, I mentioned you could package this together and make it short. So yes, I'm actually deliberately not using so much advanced tactics in this. But yes, of course, in practice, you might implement lots of different optimizations. You might have strategies for applying different kinds of rewrites, just like a normal compiler would. And then you could, in Coq, write tactics to apply them, and that would be perfectly good. Yeah, that's definitely doable and probably desirable, because you don't want to do this by hand. You would like to just say, optimize correctly, something like that. Good. Any other questions before I switch back to, yeah?
Say we wanted to run this INF program.
Yeah.
Give us such a way to do that with semantics.
Right. That is a good question. And it depends. So the question was, suppose we wanted to run this semantics. Would Coq give us a way to do that? The answer is, it really depends on how you represent the semantics in Coq. And one of the things that I'm going to argue for is that we want to represent often the semantics in a way that is executable. But there are good reasons why you sometimes don't want to do that. And actually, there's a kind of big design space of how you represent the semantics of programming languages with interesting behaviors. But the version that I'm going to tell you has this nice property of being executable, at least most of the time. So yes, so you can extract an interpreter from the semantics in addition, an executable interpreter in addition to all of this reasoning stuff as well. And essentially that is how, for instance, the CompSer compiler is implemented. You make an executable version of the compiler that you can extract and run. Great. Yeah, any other questions? Okay, so the goal for today is to sort of quickly remind you about IMP semantics and get to monads. So the first thing that we need is a model of what the IMP semantics is doing. Steve mentioned earlier that normally we think of the memory model of IMP as very simple. It takes every variable is considered a global variable. We have a total map from every possible IMP variable represented as a string I've chosen to use natural numbers rather than integers. That's because you don't have to import a library. That's also what Software Foundations does. We could pick integers. It wouldn't really make a difference to anything I'm saying. The point is that we're going to think of our IMP semantics as essentially taking in a store, which is a total function from string to nat in this particular representation, and doing some computation that involves that. Here's the concrete notation I might write for these things is, for instance, the all zero map, the map in which x maps to 3 and y maps to 120, and this one where z maps to 0, x maps to 6, and y maps to 720, this sort of thing. Okay, good. One way we can write down a semantics is with an interpreter. In Coq, it's a programming language, just like any of the others you're familiar with. So we could write an interpreter for this is for the arithmetic expression fragment of the language. And what does this do? Well, it's an evaluator. The A stands for arithmetic. It's given a memory and an arithmetic expression. It produces the natural number that arithmetic expression evaluates to. So if it's just a number, we get n. If it's an identifier like x, y, or z, we use the store to look up the value. So we had just said that the store is a function from variable names to their values. So we just invoke that function. And otherwise, we simply recurse and do the appropriate arithmetic operation. And the nice thing about setting things up like this is in Coq, the notation fixed point is how you introduce a recursive function. It tells us that the result is a nat, and we can compute with it. So if we start in that memory where x was, 3 and y was 120, then we can compute x times y and evaluate it. So this is an executable version. You could extract the code and run it as a program. This, I should say, is in contrast with the other style that we'll get to in just a second, the sort of relational, you could call it maybe the proof theoretic style of specifying the semantics. Good, okay. We could do the same thing for Booleans. Not going to really dwell on that. It's just exactly the same. One thing we do know from this is that and Steve mentioned this already, for imp, at least, it's so simple that the Boolean and arithmetic expressions are pure in the sense that they can't affect the memory. We can see that, well, we can see that if we know Coq, because Coq itself is pure and total. And so if it produces a Boolean, it can't have changed the memory M in any way. So there's sort of purity is inherited here. And that's sort of a consequence of the way we're setting things up. If we try to go down this route, however, in Coq, we run into a problem with the next step, which would be to give a denotation or a meaning or an interpreter to commands. Right, so what would this program do? Well, it would take a command, a piece of abstract syntax. It would take the starting store, which is one of these memories, and it would produce the resulting store. But of course, and this code is actually not very hard to write, right, for most of the cases. For skip, we see no changes, so the state is exactly the same. For assignment, well, we have to have some kind of notation for returning a new store where we've updated the value of the variable x to whatever we get by interpreting. We call our arithmetic interpreter to get a natural number. So this is just a function that will be the same as state except at x, where it will give us the arithmetic operation. Sequential composition is pretty straightforward. We just find the state after running C1. Let's call it ST prime. Plug that into C2, and that's the resulting state that we get out at the end. So we manually sequentially plumb the results. Conditionals are no problem. We can evaluate the Boolean with our Boolean interpreter, branch on it. This is a meta level, Coq level if then else. And so if we get a true, then we just recursively denote C1, and otherwise we denote C2. And the problem is we cannot implement while. Why is that? Well, why is that? Yeah. It's not total, right? So we could write while true do skip as an imp program. And that program would happily go into an infinite loop. And non-terminating behavior is actually one of the only sort of interesting behaviors you can get out of imp other than the effects that it has on the state. And one of the sort of necessities of doing all of our programming in dependent type theory as implemented in something like Coq or Agda or Lean is that those are all so pure that you can't write divergent computations. So you can't write an infinite loop. That would violate the soundness of them as a logic. and therefore we couldn't use them as the theorem provers that we want to do. So the problem is that the meta language Coq cannot write an infinite loop. And so if you were writing this code in something like Haskell or OCaml, there'd be no problem here. Although it's still maybe, you probably would resort to a meta level while loop or something like that. Like if your host programming language for the interpreter has a while loop, then it's easy. Coq does not, okay? So that's the sticking point, and we're going to address that in these lectures, but probably not today. But it also is related to monadic computation. But I did want to just remind you of the other approach. So why don't we get stuck if we try to do this formalization using the sort of proof theoretic style, where we have, in this case, what I've given is the judgments for a small step operational semantics. We could also have formulated the large step, and we can even prove that the large and small step operational semantics are equivalent in a certain sense. So if you're interested, you could dive into those parts of the Software Foundations development. But basically, what is the trick? Well, this is notation. I'll show you the Coq definition in a second. But this is a notation for a collection of inference rules that specify an inductive set of reasoning principles. So I guess Frank last week did an introduction to proof theory. So this is a little proof system. And any finite derivation of these rules would be intended to model the operational semantics of the INP programming language. And we can read off the various things that we saw before. So for instance, sequential composition, we just so this is a three-place relation between the input and output stores and the syntax for the command. And so this judgment says that this store st is transformed by the sequence C1, C2 into the store st double prime if we can show that C1 takes st to st double prime and C2 takes st prime to st double prime. And the trick is, let's look at what the while rule does. The while rule has two cases. It has a true case and a false case. In the false case, while is equivalent to skip, so we just relate the store to it's the same both before and after the command. And here's the thing: in the while loop, when the Boolean is true, so when it evaluates to true, we run the body of the command once to go from state to state prime, and then we use an inductive predicate where the premise is the same, more or less, starting with a different state. But the point is, we quote the entire while loop. So we unroll the loop once, that's the C, and then we restart the whole while loop again. And this is fine. This is defining a relation, an inductively defined relation. If we can find a derivation using these inference rules, what have we established? We've established that the while loop halts and provides a final state st prime. If we can't find a derivation, because while true do skip, for instance, won't have a finite derivation, we'll be sort of trying to apply this rule forever. That's fine. Relations are partial, right? They don't have to relate all states to all states or anything like that. It just means that we've sort of equated diverging programs with the absence of with the partiality of the relation that we're using to define it. Okay? So there's no issue with this. It's a perfectly good semantics, has lots of nice properties, and you can, in Software Foundations, you prove all this equivalent. Yes?
I'm not really sure if this is a well-formed question, but does this style of formalism have a name sort of in the vein, like in a proof-theoretic sense, like method reduction or secret calculus?
Yeah. Does this style, I would call this relational, relationally defined operational semantics is the way I would characterize it. So what does that mean? So this is the formal Coq definition for the syntax, for the sort of inference rules that we saw here. And I would say that what makes this relationally defined is we have, in Coq, the type prop, you should think of as the type of predicates. These are the things that can have proofs or maybe don't have proofs. And a relation is anything that is a function into prop. So in some sense, this C-eval type that we're defining here is a three-place relation where the relation is inductively defined by these constructors, which tell us how to inhabit the relation. So for instance, eSkip says for any starting store ST, well, skip relates ST to ST, is related to both of those. Okay, so these constructors will let us build essentially proof trees in the style that Frank covered last week, where the nodes in the tree are these data type constructors. Skip is a leaf, for example, because it doesn't have any recursive calls to C-eval. And basically, if we look here, if there are two premises for the sequence rule, there'll be two recursive calls. Like here's the sequence rule. There'll be two calls to this relation. Those are the inputs to this tree constructor, to this node. So in Coq, the way we represent propositions is by giving constructors that build the trees of their derivations. And there might not be such a tree, because not all of these trees exist. In particular, they all have to be finite. And so if we have while true do skip, you won't be able to find a finite tree that relates while true do skip to any states at all. Okay, so this is how you would do things in what I would call the relational operational style semantics, relationally specified. Good. Yes, question?
Can you clarify the difference between the inductive and the fixed point keyword?
Yes, good question. So inductive is defining, it's more like it defines a data type in Coq. You saw that we used it also when introducing the abstract syntax, right? So the commands and the syntax, those are just trees. They're algebraic data types or dependent data types. So inductive is used to introduce those sort of things that have constructors. They're sort of the generic dependently typed tree structured data where the nodes of the trees are these constructors. Fixed points, in contrast, like these interpreters over here, let me show you one that's actually valid. Let's go back to the one we talked about. Those are the ways of constructing inductively defined functions. So those are one of the introduction forms for an arrow type in Coq. And the thing about them is it's hidden here, but Coq must know that it's a total function. It can do that in this case because we're using a so-called structurally. So we're doing inductive, we're using, so the word inductive gets overloaded a lot, but we're using structural induction on A to define this function by pattern matching against all the possibilities. So A is one of those inductively defined data types. We eliminate it with a fixed point where we're allowed to use recursion on the subtrees. Good. We can use fixed points to construct propositions as well. So there's, but basically fixed points can construct functions of inductively defined things. Good. Okay, any other questions about this? So this is sort of the relational operational semantics. I said this was, so this was the large step version. You could give the small step version too. The small step version is, relates commands to commands and new states and so on. But partiality is sort of useful but also problematic. So there's no tree that denotes a diverging program. So that's going to be problematic because, well, not so much in IMP. As I said, the only kind of interesting properties you might care about are maybe the starting and ending stores and whether it goes into an infinite loop. But as soon as you try to look at some more intentional property, like which memory addresses were stored over time, for instance, if there happened to be a while loop that involved that, or a security policy that involved looking at the intermediate states of computation, this sort of semantics would be a lot harder to work with. It's not structural in the sense that this while rule back here, well, it's the collection of rules is inductively defined, but it's not defined inductively on the structure of the syntax, right? Because we're using while B do C as part of the syntax of the premise of the very same rule. So what that means is that all of the proofs you do for this system have to be by induction on the derivation in this data type, not induction on the structure of the term, which is often nice. You're sort of forced to use a different kind of reasoning. And moreover, because it's partial and so on, and in Coq, at least, the way things are set up, anything that constructs one of these propositions is not extractable. They get erased in the extraction to Coq, to OCaml. And so in some sense, it's not an executable program. I can't do call by name and evaluate that program represented in this semantics style. So there's some other quibbles. It's not really what I would call a deep embedding, so that means we can't sort of reuse the meta-level functionality. Like in our interpreter, we use Coq's if-then-else to implement imp's if-then-else. Here, we didn't do that at all. We just had two separate rules. We did, we sort of implemented the conditional branching ourselves rather than using Coq's version of it. Okay. So that's kind of what I want to address, and the way we're going to get there is by monads. Yeah, question?
Just regarding the drawbacks, so you said this is a big step semantics here, but if you had a small step, that would solve the first
It would solve this, and that doesn't make it executable,
but
though.
You could have a counter, right? And then because you have a way to describe every step.
So technically, so the comment was, if we did a small step semantics and we had a counter, perhaps we could make it executable. And there are ways you could go that direction, but the short of it is, because we're constructing a prop, we can't, that props get erased. And so we would have to re-implement it using a fixed point. And then we could add a fuel or a counter or something like this to say, oh, that's the decreasing. We're going to let the program run for some amount of time and then observe its behavior after that time. You could take that approach. That gets you in a different design space. As I said, there are lots of ways of implementing semantics. And in fact, you could imagine connecting that way of doing things to the step indexing, if Amal mentioned that in her so you could have a notion of approximation up to n steps. And that can all also be made to work, and you can also prove equivalences between these different formulations. But you don't get quite as nice of a decomposition semantically. You have to deal with these indices everywhere. And there are some nice things about large step semantics as opposed to small step semantics. And so what I'm going to show you is this, that we can actually kind of abstract a bit and use monads to address all of these things. So we'll have a knob that lets us turn between small step and large step observations of the program. And we'll also be able to implement a representation of diverging programs in Coq that will let us solve the problem with while. So that's, it's a different point of the design space that we've found quite nice to work with. But it also has some drawbacks that I'll get to after we've seen it. Good. Any other questions about that? Otherwise, I'm going to switch and try to get through my monad tutorial in the last 35 minutes. OK, great. So enter the monad. I had to wear this shirt today because if you have it and you're talking about monads, I think you have to, you're sort of obligated. This is a Jane Street's swag from a few years ago that I happen to like. OK, so what are monads? Does anyone want to answer? And you're not allowed to say burrito or monoid in the category of endomorphisms. Yes?
I like to think of it as a design principle. So
Okay.
it's almost more of a data structure. Not really, but I think of it more like a tree or like a dictionary or
Those,
something where it's not about the structure, it's about what you can do with it, you know?
yeah, I think I like so the comment was it's more like a data structure or a tree, or it's not about the representation, it's what you can do with it. So that is, I tend to agree with that. It's definitely more informative, at least to me, than, you know, monoid in the category of endomorphisms. Yes?
It's an overloaded semicolon and assignment operator.
Yes, overloaded semicolon and assignment. Actually, we'll see it. You're doing both a semicolon and the assignment simultaneously. So really, the two operations are overloaded let and return, if you want to think about it. Yeah, I like this idea that it's maybe some kind of data type. I like to think of it, a monad, as a data type that can represent a computational behavior. I'll say more about what that means, but we've got lots of ideas like mutable state, non-determinism, going into an infinite loop, maybe interacting with the I/O, so on. And really, the only thing that it has to support is a well-behaved notion of sequential composition. So, and I'll say more about that in a minute, but basically, all monads support is a way of computing stuff and then computing one thing after another, and that's pretty much it. But of course, the nature of the computation is described by a potentially very interesting data type. Okay, so how do we get there? I want to start from looking at this sequential part of IMP, right? So we already saw that to implement our relational semantics for IMP, we have to say when is one state sequentially related to, or after we run the sequential composition C1 followed by C2, starting from state ST, how do we know that we get in state ST prime? Well, we just sequence them, right? So we plumb the state to get a new state ST prime, and then that ST prime gets plumbed into C2 to tell us what the resulting state of after running C2 should be, and that's sort of the end-to-end behavior of this, right? And there's a couple things to notice about this. One, ST prime is, if you're familiar with Coq, it's what's called an existential variable. It's actually hidden, sort of if we look at the conclusion of this as a rule, right? ST prime doesn't show up anywhere here. It's internal state. It's the midpoint of the computation. And there's this explicit plumbing, right? We had to make up this name ST prime as part of that, to name it. If we tried the same sort of thing with our fixed point version, not the relational version, where we were now taking a command and trying to give a mem to mem function. If I sort of uncurry things, what does this look like? Well, we're trying to denote the sequential composition of C1 followed by C2. So what does it need to do? It has to be, it has to take in the initial state, ST. We need to somehow name or get our hands on this intermediate state, ST prime. How do we do that? Well, we call our interpreter on C1 and ST, and let's name it ST prime. And then we explicitly plumb that into C2, and that's the final state that we get out at the end, okay? So that's the sequential part, and the part down here is like we don't have a way of doing this with wild. This type, mem or a mem in Coq, denotes total functions, so that we're not going to solve while with just sequential composition. We'll have to be a little smarter about that. But let's focus on just this bit for the moment. So we're going to start with just abstracting this sequential composition of stateful functions. And if you're interested in looking into the full version, I'm skipping over several other useful instances of monads that will give you more ways of generalizing this idea. But basically what we're going to do is, as someone suggested, abstract over the sequencing, the semicolon operation. And the important thing is we need to name this intermediate state. And when we see that, the result of this computation is going to be some intermediate state that we're going to bind in the second computation. And in fact, notice that the result of this whole thing is some third state, st double prime. We're going to be able to return that as an answer in general. And we could lift this behavior to lots of different things. So here's another slight variant of imp where we can have all these commands, but we could add a command that lets us return a value, for instance. So if you think about what this program would do, intuitively, it's going to do some imperative updates to the state, and maybe also return another value. In this case, y will be x factorial, so 120 in this particular case. This is just the usual, what if imp had a return statement? We would need to feed its answer back somewhere else. In this case, it wouldn't be enough to model this program as a function from memory to memory because it also returns some extra thing in addition to doing all the updates of the memory. So in this case, our semantics would have to look more like, give me the starting state. I'll return the final state along with whatever auxiliary answer you computed based on that starting state. Okay? So that's the step we need to do to sort of abstract all of this into, we'll call it a state monad. So a state monad, I'm going to call it state of S, where S here is just some arbitrary parameter. Returning an answer of type B is going to be just S arrow S cross B. So we just saw, for instance, that if we have a stateful computation like an imp program that returns a natural number, well, that's a mem arrow mem cross nat. And if it didn't return anything interesting, like it didn't have a return or just had a return void kind of thing, well, we could use unit instead of B to sort of say there's an uninteresting result. But for states, the important thing is that the pattern is you take an input memory and you compute the final memory out. Okay? And we can abstract over the particulars memory. We could augment imp with some fancier version of memory, maybe one that also tracks labels, and so it would be of a different type. Or we could use a structured memory that you can allocate data structures into and that sort of thing. And we have also abstracted over the type of results. Now we can look at, if we had this sort of notion of composition, we can look at what our function did in coq, right? In coq, we took in the initial state. We computed some denotation using that initial state. Well, if C1 is one of these memory arrow memory cross answer functions, well, we can use coq's meta level let to extract the intermediate function, intermediate state. The intermediate command always returns a unit value. It's very uninteresting. Skip doesn't give us any result. There's no return. So we can just ignore that part. And then we can call C2 on that intermediate state. Okay? So if we name that operation that does this plumbing of naming the intermediate state, we're going to call it, I'm going to call it state bind, because this is going to become the generalization of semicolon for general monads. What does it look like? It looks like this. It takes in state of SA. So this is a monadic computation in state. That's just S arrow S cross A. It takes in a continuation, K, which we can see over here in my previous slide, is the continuation is the second command of the sequence, because that's what a sequence does. That has to be a function of the result of the first thing. Why? Because we're using let at the meta level to name that intermediate thing. And then we just call, so what does the bind do for state? We call the function on the initial state. We name the subcomponents. We call the continuation on the intermediate result and the intermediate state. That's really all there is to it for the state monad. And then we make an observation that it's nicer to write some notation that looks like this, where we say that rather than saying state underscore bind of M in a continuation fun x arrow body, we write that like this using the so-called monadic arrow notation, where we say let x be M and then run the body. Okay, and I think that the right way to think about monads is really just a generalization of let, right? So normal in vanilla old standard Coq and in OCaml and in Haskell and lots of other functional programming languages, you have some kind of notation for a pure let where you name the result of some computation and then you call the rest on, you can use it in some scope. And so for the explicit state where we passed the plumbing ourselves, we let bind the result of the computation, and then we call the rest on X. And notice all these parts that are sort of in blue, those are part of the type of the monad. So those are the auxiliary parts of the data structure that are defining what makes state different from non-determinism or other instances of monad. They're sort of the data structure that helps us define the plumbing we need to implement sequentiality. But under the hood, it's really just this let that's going on. And then we can abstract away from the details of the monad. The important things here are the computation M, the intermediate result X, and what you do with that X in the rest of the computation. And that's how we get to bind. And then we just give a slightly different syntax because we like that notation rather than this one. So that we've played a couple of tricks here. One is, I should pause and ask if there are any questions about this. Yes?
Just to be clear, in case I missed something, the type of REST-X is a function from state to state?
Yeah, the type of REST-X is going to be a function from whatever the result of whatever X is. Let's say it's B. And then it will take that and return, in this particular, in the state case, it will be memory arrow, memory cross B. And let me, so you're basically asking what is the signature, if we sort of generalize this, what are the types of these different things? And let's get there. So let me switch to this slide first. So the type of bind, which is what you're asking about, it takes a monadic, so M is for any monad. We were just considering the state monad. It takes an M that returns an answer A, so an arbitrary monadic computation returning A. The rest is a function of that intermediate value producing a computation which is in the same monad. So in that case, it was a stateful monad, which is itself a memory arrow, memory cross B function. And then it has to produce a computation in the result type. So that's what bind is. And for state, it looks like this, right? So bind, just to instantiate all that, it takes, so if we name state S, that's our M, right? So we have M of A, we have A to M of B, and then this whole thing has to return M of B, which is itself a function. I think a lot of the confusion is, you have lots of different functions going on here, and if you sort of unfold the definition of state, there's another function besides the one in the continuation. There's the one in the data type that implements it. Good. We can also implement return. So what does it mean to return an answer in a given state? Well, it has to be a computation. So to return an A and produce an answer in a given state, well, it has to take in the state and just leave it unchanged and just pair it with the answer. So this is the the way that you return an answer out of state is just by giving the state unchanged, and we could define notation for that. And really what a monad does is just those two things. We abstract over this data type of what it means to compute. We'll see several others in the upcoming lectures, and I'll give you a few more examples in just a minute. And it has to satisfy this interface of return and bind. But in exchange, every different choice of monad provides more computational behaviors that are interesting to work with. So why do we want state? Is so we can read and write locations in the imp store. And so the monadic computation for imp-style states will provide operations that go beyond just being able to do sequential computation. They'll be able to load and store values from the imp state. So what do those look like? Well, they look like get and put. So if we want to get the value of the current state, and here this is reading the entire store, so it's just returning the result. And if we put the value as we update the state, well, it doesn't matter what the initial state is. The new state is what we put there, and there's no useful answer. So the result of that intermediate computation is just unit. But notice that we are plumbing the state through kind of under the hood in these implementations of get and put. And notice their types. Get is a monadic computation that returns the very type of the state that you're accessing. Given an initial state S, put S is, sigma, put sigma is itself a computation that will update the state and return unit. Question, yeah?
I'm a bit confused about the return on the previous slide, because it seems more like return allows us to create basically a monad with a particular input A. It's not really about returning.
Yes, so the comment is return seems to be creating a monad with a particular A, not somehow otherwise doing something. The way I would phrase that is so a monad isn't a computation. The things of type state SA, I would say that's a monadic computation. So we're not creating a monad by doing this. You can think of it as returning will allow some further sequential computation to access the thing that we returned, right? So, and we'll see that in a minute. If I return 3 and then bind that computation with some other stateful computation, that other computation will have access to the 3. So return is, I guess, chosen for, it is a terminal state of in some sense because it gives you the result of the computation. People also talk about this as it lifts the A in a pure way into the monad, that sort of thing. That's another kind of intuition that you can use. But in some sense, you're going to have a bunch of lets, and then you need to say, how do you end your sequential computation? You end it by returning an answer to the context that could then do something with it. So the return comes from that view of sequentiality more than anything else. Yeah, another question.
Yeah, regarding what you have at the bottom of this slide, is there any reason to make that a notation when it already just looks like applying the function?
Is there any reason to make this a notation when it already looks like applying the function as it here? Yes, so in this case, if we just cared about state and state was implemented as a function, then we could use this, and we could just call it state ret A or whatever. But not all monads will be implemented as functions, and so you need to have some notion of returning. It might involve building a tree structure or making another data type. And so this is going to allow us to overload this notation to use in other contexts. But yeah, that's a good observation. Yeah.
So on the next slide, when you talk about put, that's not like, is it really updating the state or is it just replacing it entirely?
Well, so the question is it really updating the state or is it replacing it entirely? It's a matter of perspective, right? So it's replacing the entire state. in this version of things, right? So this put operation throws away the old initial state and says the new state after a put is this whole thing here. So this alone is not enough to do imp semantics, because you can, well, you would need to do some extra programming to modify just the x location of the state. If we instantiate s to be mem for our imp semantics, then the updated version would be, we would have to implement x gets 3 using the put operation, but we have to do a bit of work to do that. It's not just call put on 3, because we need to say that it's x that's being updated. Yeah. Good. All right, so this is what all monads provide, just sequential composition. Specific monads give you monadic operations like get and put. And then to make things a little bit, so this is a Coq-specific detail, but it's useful. So in Coq, when I declare this class of monads, this is like a type class, if you're familiar with Haskell, or you can think of it as just the interface for monads. And then you can have different implementations that satisfy this interface. And the way that I just wanted to show you one example of how you do that in Coq is we have all these definitions from before. We can just say that, and I renamed it, so we have state, that's our type for implementing the monad. And we can say that state of S is an instance of monad for any S by just basically copying and pasting our definitions of return and bind as the implementations of those methods. And then we can have some, and then get and put, we can define separately as here. So this is just an overloading mechanism, so we'll be able to use return and bind kind of generically for any monad, including state.
I'm wondering if you could speak to the advantages and disadvantages from an engineering perspective of having the monad laws in that class, because I see you did.
Yes. OK, so this is a little bit of a technical thing in Coq. We'll get to the monad laws in just a minute. And they're very important, and in fact, will feature in quite a bit of the lectures. But so this is just the data types and the operations that define a monad. To be considered a true monad, it will have to satisfy some laws that I'll try to get through in the next 10, 12 minutes. And the question was, we could put those laws here if we wanted and sort of include them as part of this. I think in Coq it's considered best practice to sort of unbundle your operations from the proof component. And so that's what I've done here. Basically, that means that these are the parts that if we were to extract from the program, we could run them. The laws are more about the reasoning, and they build up proofs that we probably don't care about extraction. So if we just need a piece of the program that uses the the implementation of these things, we don't have to sort of bundle together all of the proofs that go with them. But that is a good design. It is a bit of a design choice. And just if you look at the full development, you can see by picking different implementations, you can pick other kinds of monads. And there's lots of monad tutorials out there. I want to get on to reasoning about monads. The identity transformation on a type is a monad. Option is a monad. There's several different ways to implement non-determinism. List by itself is a monad with a sort of ordering on results. If we take a finite set of A's, that's a non-determinism monad. And in Coq, you can sort of existentially defined non-deterministic propositions, which you can think of as A arrow prop, sort of sets of A's that might be defined by perhaps uncomputable predicates. Those are also a monad. Yeah.
So you said a few slides back that the monad is a well-behaved sequential composition. Does this mean that it's hard to model concurrency and other effects using monads?
So the question is, it's a well-behaved sequential composition, and is it hard to model concurrency? There's a couple of different, there's a long answer to that. The short answer is yes, it's pretty there's a criticism of monads if you're trying to use them to model concurrency, that they over-serialize the computation. That's the short answer. The long answer is there are various ways of shoehorning concurrency-like behaviors into monads. There's something called the poor man's concurrency monad, and there's various sort of fancy data structures that you can get concurrency-like behavior in it, but that's going to sort of take us a little far afield. So short answer, they do over-serialize, and you might want to relax these things if you want to deal with concurrency. That said, I still think that even concurrent programs can be thought up of interleaving sequential programs, depending on for some notion of atomicity for those sequential parts. And so for those sequential pieces, you probably will want some kind of monadic thing anyway. So you have to maybe do a lot of work to add concurrency on top of this. Good. So we do need to ask this whole question of what does it mean to be well-behaved sequential composition. So in IMP or in your favorite programming language, semicolon is associative. So sequential composition, it doesn't matter what order you parenthesize things. And if I was claiming that really sequentialization is more like, or monadic bind is like a generalized let, those are also associative, right? If I say let x equal, and then I put in the body there, let y equal something, and then I use x in its scope and I use y in its scope, I can always hoist the definition of y outside the definition of x and reassociate those lets like this. This is sometimes called let floating or let hoisting. That's really the notion of associativity that, that monads give you, right? So it's just the idea that if you have a let that's defined in terms of a let, the inner let can be hoisted in front of the first one without changing the meaning of the program, okay? So that you can, these will both evaluate to the same thing in any well-behaved program. And so we can capture this as a law. This is just writing all that formally. What does it mean to be associative? So this is using the bind notation to make it a little bit nicer. But it's basically saying if we bind x to the result of binding y to the result of, and so on, we can always pull the y outside. And the scoping works out. We can use y inside of the inside of the definition of x, that's just fine. And we can use x inside of the result of the whole thing. But we can't use y inside of there. The scoping prevents you from, y is not in scope in the continuation C here. It's only in scope in KB, but that's fine. So we have to prove that. We can think of this, so the next law we can think of as just substitution, right? If we get to a point where we know that we have a value, so we've returned a value in one of these computations, we can substitute. So let y be the pure computation result 3. Well, we can replace the uses of y by 3 in the later parts of the program. This is, and that's equivalent to, substitution. So that is called the bind left law. It says that if you bind an answer x to the result of a computation that just returns a and does nothing else, so this is the equivalent of let x be 3. Well, that's equivalent to just calling the continuation on 3. Right, so this is a substitution principle. When you get down to a value, you can replace the uses by the value. And so that's one. And then the other one is, well, if you just return x itself after naming it, well, that's equivalent to not doing anything at all. So these two computations where you say, well, let x be m in x is the same as running m without naming that result anywhere. And so that's the monad right law, which just says if you run the computation m, name the result x, and then return it, that's the same as running the computation m, which is going to return x anyway. So you don't have to bother naming. So those are the monad laws. And they make perfect sense when you think of them as like sequential composition and substituting equals for equals. But I went through them pretty quickly. So let me we can package those together as a separate type class. These are the proofs that we need to prove that something is a monad. And I'll let these pause here while I pause for questions. Right, so if we want to, oh yeah, good.
When you let float, sometimes you do capture avoiding substitution when there are name functions. How do the monad laws do that?
Right, so the monad laws, I mean, if you look at, that would be here, right? It's our obligation to prove that you've done the right thing with whatever substitution you're implementing as your bind to make sure that this equation holds, which basically tells you that that y, so the scope of y can only be sort of kb here. So if your implementation of bind were incorrect and somehow this had a different behavior because y could be used in kc somehow, then it would fail to satisfy this monad law, and you wouldn't have, so basically, in order to prove this law, you have to prove that you've done the capture avoiding substitution that you want to avoid. Does that make sense?
Yeah, how do you do that? Can you just say it's not the free variable?
Well, so the way that it works depends on the monad, right? And there's no need to reason about free variables or anything like that. Remember, these MAs and so on for state, for instance, are just functions. So ultimately, it just boils down to, is this representation, when you unfold the definition of bind, equivalent to that one? And it might take some hard work to prove that, but effectively, those proofs are about the implementation of the representation of the monad, like the states as functions. And that may need some, typically you don't need to assume anything about freshness of variables or free variables or anything like that. You're just reasoning purely about the functions themselves. If that makes sense. There are actually quite a few subtle things going on here. Maybe this is, I have 2 more minutes, so I'll leave you with the, a couple of things we can do. Well, already, let me say, once we have these monad laws, we can, prove program equivalences, kind of like the one I showed you at the beginning with imp. So here's a monadic computation. It says, let y be return 3, in return y plus y, let x be that, and multiply it by 2. You can use the monad laws to prove that this is equal to return 12. So you can sort of simulate the computation. So that's one thing you can do. And a lot of what we're going to talk about starting tomorrow is, what does this equals mean? Because for this particular, well, for state, for example, we picked state of SA to be functions. And now if you kind of unfold all the definitions, like ultimately, we're saying that some monadic computation, which is a function on memories, is equal somehow to some other monadic computation, which is also a function on memories. And that's not a trivial thing. You might want to use something like functional extensionality, which says, 2 functions are equal. Notice that they have function type. F and G are equal. If when you give them all inputs, they give you this, give them the same input, they give you the same output. But that's not necessarily the right way to go about reasoning about the equivalences of all of these things. So the real question is, how do we capture behavioral equivalence, which is really what this equality is getting at? When are 2 stateful computations equivalent? And to make progress there, we're going to introduce another type class. I'll call it EQM for sort of the equivalence of some monadic computation. And we're going to insist that every monadic computation, in addition to satisfying all those monad laws, they satisfy it up to this notion of equivalence instead. That's going to be the key sort of move that A, will connect it to all of those logical relation things that Amal was talking about last week, but B, will let us do proofs of reasoning about behaviors in a very nice way that we'll see tomorrow. So I'll remind you why we want to do that tomorrow, but basically the upshot is, rather than use equal, we use this sort of parameterized equivalence, and hint, that comes with a little bit of work. We're going to have to prove, for example, that our bind represents that notion of equivalence, which I'll show you tomorrow is itself a logical relation on this type. So if you want to think about that between now and then, that would be a fun puzzle. And we'll pick up there tomorrow to see how that's a useful step towards doing more interesting reasoning about computational behaviors. Thanks.